let's do the determinants. Of course, I'm not going to do the detailed detailed computation for the determinant, but let's just compute for it here. So this is now equal to this one. So this is K minus M omega squared times this minus times this. So this is 2K minus M omega squared times K minus M omega squared minus K squared. Okay, and then this K times multiply minus multiply. This is plus K times K minus M omega squared. Then 0 equals 0. Okay, so this can now be simplified further, and the final form, or the simplified form, would look like this. This is omega squared times K minus M omega squared times small m, capital M, omega squared minus 2 mk minus k, capital M, equals 0. Okay, so this is three factors, which corresponds to our three characteristic frequencies. So the following expression for your omega are the following. First one, omega 1 is equal to 0 from here. Okay, now if we're going to substitute that, okay, here or here, okay, so let me select this, then let's paste it here. Sorry. Okay. Okay. Now, so let's substitute omega 1 here. So this is 0, this is 0, and this is 0. Okay, so we end up with K A1 minus K A2 equals 0. Okay, so what does it mean? It means that A1 is equal to A2. Again, substituting this here, we end up with negative K A1 plus 2 K A2 minus K A3 equals 0. So this is now equal to, okay, sorry. So K will cancel. A1 is equal to A2. So this is A1 Okay, so this is A1. This is A1 minus A3 equals 0, or simply A1 equals A3. Okay, so if we're going to use this term, I use this figure. Let's copy this and let's paste it here. Okay, so the resulting equation becomes A1 is equal to A2 and it's equal to A3. Okay, so the resulting motion is that when the left and the right particle move to the right with equal amounts x1 and x2, x3, x2 will follow. So the resulting motion is a pure translation. And that's precisely why omega is 0. If omega is 0, that means there is no oscillation. Because remember that omega describes your oscillation. If that is equal to 0, therefore there's no oscillation. And the only thing that will, the only motion that is possible for a one-dimensional molecule like this is just pure translation. Either the molecule altogether move to the left, or all the particles or the whole molecule will move to the right. Okay? Okay. So let's move to the second omega. And let's get it from here. So from here, omega, let's call this omega 2. And that is equal to, if this is equal to 0, so omega squared is equal to k over m. So omega 2 would be square root of k over m. Okay, so from here, again, so that means omega squared is k over m. So if you're going to substitute it here, so omega squared is k over m, so this is negative k a1. And then plus k a2 minus k a2 equals 0. Oh, sorry, this should be 1. So this 2 will cancel. So therefore, A2 is equal to 0. Next, in equation number 3, sorry, this should be A2. Sorry about that. Should be A2. Yeah. That should be A2. Okay. Because A2 is equal to 0, so this is cancelled. This is cancelled. So the only thing that remains, or the only terms that remain, is negative k a1 and minus k a3, and this is equal to 0. So the result here is that a1 is equal to a3. we're going to substitute this to the third equation, you'll end up with A2 equals 0. So, what does the motion look like? Okay, so in this case, A2 is equal to 0. So that means the central particle remains the same, similar to what we had earlier. A1 and A2 are moving in opposite direction. So if the particle moves to the right, this particle will move to the left with equal motion. So this moves here, this moves here, moves like this. This particle stays there. Okay? Sometimes we call this your asymmetrical move, or the second move. Okay, so this is stationary.